Okay, the last lesson in your workbook. We're going to look at some final integration techniques. These are a little bit more obscure, different, and just somewhat weird. But you can always add or subtract terms in the numerator, or multiply both the numerator and denominator by a common factor to make integration possible. So in this particular example, notice how I have 2x over x squared plus 2x plus 1. And if I actually did u substitution, and don't write this down, but if I did do u substitution, you'll see that the derivative du dx is equal to 2x plus 2. I don't have 2x plus 2, do I? I just have 2x. So what you can do in this case is actually add 2 and also take away 2 in the numerator. And if I do that, watch, because then I can split this up as 2x plus 2 all over x squared plus 2x plus 1 dx, and then minus the integral of 2 over x squared plus 2x plus 1 dx. Now, that information I did earlier about the u substitution, hey, that now works for the first integral. So if you do this, you'll just get the integral of 2x plus 2 over u, and I think dx just becomes du over 2x plus 2. Perfect. The integration of 1 over u du, and of course that's just natural log of u, which is just x squared plus 2x plus 1. I guess I should put absolute values just to make sure. The integral on the right, however, is not as easy, but hopefully you can see that the denominator can factor into x plus 1 all squared, which means I can rewrite this as 2 the integral of x plus 1 to the negative 2 dx. And if I anti-differentiate that, I'll just get x plus 1 to the negative 1 over negative 1. Maybe I'll combine that with that negative 2 to make this a positive 2, just to save me some space. And then plus c. There you have it. So here was an example of where we had to actually add and subtract the number in the numerator. Okay. Now, we could do the same thing for example number 2. Or you can try this other technique of actually multiplying the numerator and denominator by a common factor. So I'll show you both actually for this one. Method 1 would be where I'm going to ask you to think about, what can I do with this? And if I said once again let u equal to e to the x plus 1, I'm looking for du dx being also e to the x. And I don't have that. So what can we do? How about going 1 and then adding e to the x, and then subtracting an e to the x all over e to the x plus 1 dx. Now why is that nice? Because look what I can do now. I'll separate it again, and I'll say 1 plus e to the x over e to the x plus 1 minus the integral of e to the x over e to the x plus 1. You see how this is nice? The integral on the left, those two things are the same, both in the numerator and denominator, that's just equal to 1. And the integral on the right then allows us to use this u substitution. U du. And so if I anti-differentiate now, I get x minus natural log of u, which is just e to the x plus 1, plus c. Done. I forgot my equal sign, sorry. Equal. If you don't like that method, we can try method number 2, which illustrates this thing called multiplying both the numerator and denominator by a common factor. And if I multiplied both the numerator and denominator by e to the negative x, look what happens here. I'll get e to the negative x, and then I get 1 plus e to the negative x in the denominator. Notice now I can just let u equal to e to the negative, 1 plus e to the negative x in the denominator. Du dx just becomes negative e to the negative x, and that just happens to be my numerator, du negative e to the negative x. So this just becomes e to the negative x over u du over e to the negative x with a negative. Divide out, a negative 1 over u du. That's nice because that just gives us natural log of 1 plus e to the negative x plus c. Pause. And although these two final answers look different, if you actually brought your graphing calculator and graph those two functions, you'll see that they are actually the same. Let me try to just quickly show you that to you now. And so the forms are different, but nonetheless they are the same. Absolute value e to the x, close the bracket, plus 1, close the absolute value bracket, close the ln bracket. That's x1. Here's y2 negative ln with the absolute value 1 plus e to the power of negative x. Close that, close that, close that. Can I change this to a different feature? Nope. I should change this to a different feature. Let's make that darker. Here we go. Graph. Oops. Change my window. Zoom. Zoom. Sorry. Let's try a better graph. Let's go zoom standard. Better now. There's your first one. Here's the second one. Exact same graph. And if I give you my table, you'll see that the values of x and y, the y values are the same for both. Okay? Alright. Now, sometimes you're going to have to use trig substitutions. Once again, going back to pre-calc 12 days. Okay? Remember we did sine squared plus cosine squared equals to 1? Well, there's other ones you can use too, like tangent squared x, which equals to secant squared x minus 1. And cotangent squared x, which is cosecant squared x minus 1. Why is that helpful? Well, example 3 shows you why. Because the tangent 2x can be written as secant squared 2x minus 1. And the cotangent x can be written as cosecant squared x minus 1. And why is this helpful to us? Well, because the antiderivative of secant, I hope you remember, is just tangent. This is a 2x, so there will be a 1/2 factor in front. The antiderivative of minus 1 is negative x. With cosecant, I should have said cosecant 3x. The antiderivative of cosecant is negative cotangent squared of 3x. And once again, I need an extra factor of 1/3 in front. That's the chain rule portion. And with another negative 1, the antiderivative of that is minus x plus c. So really, by changing them, we found pretty straightforward antiderivatives. Remember those trig ones you were supposed to memorize? That's why this one's weird too. Okay. Now, sometimes you're going to get things like this, where I'm asking you for the integral of the absolute value of these functions. Now, remember back in grade 11 when you did absolute value functions? What happened to the stuff that was below the x-axis? You are correct. It got flipped up and made positive. So what I'm drawing here in red is the absolute value of x squared minus x minus x. Now notice here too that there are these points where it crosses the x-axis, looking at -2 and also 3. So in essence, you have to actually separate this into 3 separate integrals. So the part in blue would be the antiderivative, or the integral from -3 to -2 of the function x squared minus x minus 6 dx. If I want to do that green portion, you can see that's the integral from -2 to 3, but now you'd be doing the negative of that graph because you flipped it around. And then finally that last portion from 3 to 5, that once again is the positive portion of the graph, and that is what you would have to do. Okay? Alright. Turn the page. So once again, there are many techniques for integration. And this course only deals with the most common of them all. When integrating, please explore options until you find one that works. And you might want to practice fitting the integrands into basic integration formulas that you have memorized or will have memorized. So looking at number 5, this looks really scary. E to the -3x with the sign of that function. But I hope you remember that this is one where you can divide into 2 separate functions. The integral of sine e to the -3x over e to the 3x minus e to the x over e to the 3x. And this is helpful because the integral on the left, I'm thinking you can use substitution, where the one on the right simplifies just to e to the -2x. So, I will ask you to separate this. And can you do some u substitution to help you figure this out? So for this one, I'd suggest let u equals to e to the -3x. For this part over here, I suggest let u equal to just -2x. And then go ahead and try to find these antiderivatives. And I will tell you the answer because I want you to try it and I want you to get it. It's just going to be this 1/3 cos e to the -3x, and this part becomes 1/2 e to the -2x, and don't forget plus c. Okay? Now for number 6, with all this cosine and sine and business like this, I suggest you make a u substitution as well. I would suggest in this case this ugly part here with the square, taking all of that as u. So du dx is just the derivative of natural log, which is 1 over sine x. But don't forget the derivative of the inside is cosine x. And once again, I'm going to let you do the rest. I will just quickly tell you that the answer is natural log sine x all cubed over 3 plus c. Now once again, don't just copy the answer down. You definitely need to practice making this work for you. And so please, please, please go and do it and then double check your answer with mine. Okay? Now one last one that I'll do for this section. Remember that if integrals involve radicals and you can't seem to find the integrand that works into any basic integration function, then once again It's U substitution to the rescue. In this particular example, how about letting U equals the stuff underneath the square root? The derivative du dx is just equal to 1, so that just means du equals to dx. And so if we just quickly did that, this will become the square root of u du, and you still have an x plus 2 in the numerator. And so the only way we can get rid of that x plus 2 is to really just solve for x from here. So x is actually equal to u minus 1. So now replace x with u minus 1 plus 2 over root u du, which of course equals to the integral of u plus 1 over root u du. And then we can actually separate this into u over root u plus 1 over root u du. And then we can simplify that into u to the half plus u to the negative 1/2 du. And now you're ready to anti-differentiate. Dot, dot, dot. Because just like the other ones, I'm not going to show you the work at this part. But I will show you the answer because I know you're going to do this, right? And when you do it, hello, final answer. Wow. Can you say practice? Say practice. Can you say do all the problems in assignment 9.7? Yes, do all the problems in assignment 9.7.